Okay, so last time we already discussed the valence split due to the overlapping of atoms orbitals, and when numerous atoms come closer, these orbitals will be overlapped, and the valence electron will split to different energy level, and the full field with the electrons called the valence band and the empty conduction band. Okay, and the gap between these two bands called the band gap. Okay, and for the metals or alloys, these two bands are overlapped. Okay, tightly contact with each other or overlapped. Therefore, the electron can jump to from valence band to conduction band easily, right? Because there's no gap, no barrier. Okay, the charge carrier can jump from the valence band to conduction band easily. And for the semiconductor, because it is lack of free electron, okay, lack of free electron, and the band gap between the conduction and valence band is large than the metals. Okay, therefore we need external energy like thermal energy to push those charge carriers jump from valence band to conduction band. Okay, so there's a gap, a larger gap between these two bands. Therefore, we need the external energy to promote the charge carrier jump from valence band to conduction band. Okay, and through the insulator, the band gap is larger than that of the semiconductor. Okay, therefore, if we want the insulator to be conductive, we need extremely higher external energy to promote the electron jump from valence band to conduction band. Okay. Okay, so the scheme of the conduction of metals. Therefore, we need a thermal energy, the external energy. For example, thermal energy puts many electron jumps into higher energy states. Okay, for metals, for conductor. Okay, for conductor. However, if there's no external energy, metal is still very conductive, right? Because these two bands, conduction and valence band, are overlapped. Okay, so for energy states, for metals, nearby energy states are accessible by thermal fluctuations. Okay, and for semiconductor and insulators, the band gap is larger than that of the metals, right? And for semiconductor, there's a band gap between the valence and the conduction band. Okay, therefore we apply external energy to make the field valence band, the electron field valence band, or the charge carrier field valence band, to jump from the valence band to conduction band. Okay, and through this insulator, okay, the gap between these two bands are much larger than that of semiconductors, right? Therefore, we need a very high external energy to promote the electron or charge carriers jump from valence band to conduction band. If this external energy is not high enough, well, the charge carriers cannot reach the higher energy level. Okay, therefore the electron will return. They cannot jump to the conduction band. Okay. Okay, so this is the idea that we already mentioned, that the charge carriers need to be excited by external energy for semiconductors and the insulators, especially for semiconductors. Okay, we need an external excitation to promote the electron jump from valence to conduction band, and one hole remain in valence band or in valence band. Okay, and move at different speed that we already mentioned previously. It's called the drift velocity. Okay, drift velocity. And the higher temperature promotes more electrons into the conduction band. Okay, therefore, the conductivity increase as the temperature increase. And electrons scattered by impurity, grain boundaries, and so on. So that means those defect, point defect, line defect, or area defects will reduce the conductivity of metals or of materials. Okay, so last time I already mentioned this main free path, that is the charge carrier, the main free path of a charge carrier as its average path that's between collision. And also we already discussed about the temperature effect, the resistivity as a function of temperature. While this function comes from experiments. Okay, from this experiment we already mentioned. Our previous course we already mentioned this experiment. Okay, so we get coefficient called the temperature coefficient of resistance at a specific temperature. Okay, we can find out that for metals, the temperature coefficient of resistance is positive. That means when the temperature increase, the resistance increase. Okay, and for those temperature coefficient of resistance is temperature coefficient of resistance is negative. That means that the when temperature increase, the resistance decrease. Okay, especially for semiconductor. Okay, especially for semiconductor. Okay, that means the higher temperature makes the semiconductor's conductivity increase. Okay, so this is a consistence that we need external energy to promote more free electron form in the semiconductor. Okay, so the conductivity of metals affected by the imperfection. Okay, the imperfection. A perfect crystal always has the highest conductivity. Therefore, for the electronics industry, we always want to fabricate very pure and the perfect crystal metals. Okay, we need for example, we need a very pure, high purity copper, right? Because we need a very high conductivity. Okay, therefore for the perfect crystal, figure A, the electron will move freely without any barrier. Okay, without any barrier. Okay, and the figure B shows what? A crystal heated to a high temperature, at an elevated temperature. Okay, so when the metals heat up at an elevated temperature, its conductivity will decrease. Okay, that means its resistivity will increase, right? So it's consistent with the result from the temperature coefficient of a resistance, right? Because when the temperature, because when the metals is heat up at an elevated temperature, its lattice start to vibrate. Okay, its lattice start to vibrate to make higher resistance, to make the more barriers to retard this electron movement, right? So when the temperature at higher, when the metals is heat up at a higher temperature, the electron, well, it cannot move freely because the lattice is evaporated or distorted to make more barrier. It's like we are working in a straight line or straight street, or we are rendering passing through the no, like a maze. Okay, like a maze. Okay, so in Figure C, it shows the defect, atomic level defect. Okay, atomic level defect. Okay, so there's some vacancies or interstitials, atoms or substitutional atoms, whatever. And those imperfection here will be a barrier to retard this electron movement, okay, and reduce the conductivity. Okay, therefore the effect of atomic level defect, imperfections in crystal structure scatter electrons. Okay, and reduce the mobility and reduce conductivity. And defects include solid solutions, vacancies, dislocations, and grain boundaries. Okay, and the overall resistivity can be written as this. So it's already mentioned previously is the resistance as a function of temperature. Okay, and this is a resistance as a function of impurity. Impurity or some defects. Okay, and this defect could be solid solution, vacancy, dislocation, and grain boundaries. Point defect, line defect, or area defect. Okay, and it's an experimental function. Okay, it's an experimental function. Okay, and the B is a constant defect resistivity coefficient depending on the type of defects. Okay. Okay, therefore the overall resistivity of the materials or metals can be shown in this figure. It's a summation of resistivity as a function of temperature and the resistivity as a function of defect. Okay, and the effect of processing and the strengthening, okay, includes the cold working, strength hardening, and the grain size control that will reduce the conductivity. And age hardening and dispersion strengthening reduces the conductivity more, but not as much as a solid solution strength. Okay, therefore the resistivity dominates by the defects and temperature. And the defect includes the point defect, line defect, and the area defect. Okay. Okay, so let's look at the deformation. Right, deformation creates what kind of defect is? Line defect, mostly the dislocation, right? So do you remember we at the tensor test or we are bending metals, the dislocation density increase. Okay. Therefore, the figure shows the conductivity correlated to the deformation and the impurity, point defect. Okay, and the point defect. So you can see for the pure metal, well, the deformation, well, may not affect it a lot, right? However, for the copper dope with different impurities, its conductivity drop substantially, right? You can see it's the is the pure metal. When there's some impurity doped, you see this conductivity drop substantially, right? Right. And also, we can look at the figure shows the conductivity correlated to the addition of impurity atoms. Okay, so when the impurity additions increase and the conductivity drop significantly. Okay, therefore the conductivity of alloys, that alloys has much higher resistivity than pure metals due to additional scattering. We already mentioned previously those addition of impurity will be regarded as the barriers to make the scatter, okay, electron scatter, okay, and reduce its conductivity. Also, alloy resistivity tend to be stable with temperature. Okay, then the pure metal, okay, alloy resistivity is more stable with temperature. Okay, with temperature. And high resistance alloys can be used to make heating elements. Okay, because its resistance is higher, and when we apply the higher current, that means it can produce the higher thermal energy. Okay, produce higher thermal energy. Therefore, we can conclude that the resistivity of metal, especially for metals, is dominated by three factors: thermal, that means temperature, and impurity, and the deformation. Okay. In previous slide, we say the resistivity of metal dominates by resistivity as a function of temperature and as a function of defects, right? And this is a defect. The defects can be classified into impurity and deformation. Okay, so this two is the resistivity as a function of defect. Okay, so the grain boundary is area defect. Dislocations is dislocations are linear defect, impurity atoms, and vacancies a point defect. This acts to scatter electrons so that they take a less direction pass, less direct pass. Okay, less direct pass. That's mean more barriers to the electron movement. Okay. Okay. So, and this figure shows the resistivity correlated to temperature and the impurities and deformations. Okay, so it's a linear relations between the resistivity and temperature correlated to the impurities and deformation. Okay. So we can estimate the electric conductivity of copper nickel alloy that has the yield stress of 125 megapascal. It's from experiment. It's for experiment. Therefore, these two figures shows the mechanical property and electrical property of metals or alloys. Okay, so what's these two figures tells us? Does this two figure tell us? That means when we have more higher impurity content, its mechanical property, such as yield stress, enhanced, right? However, its conductivity decreased. Okay, conductivity decrease with higher concentration of those impurity atoms. Okay, so if we get a higher content of nickel, we get a higher urine stress, right? And also we get a higher resistivity with the higher content of nickel impurity atoms. Okay, that means its conductivity reduced. Okay, conductivity reduced. Therefore, mechanical properties and electrical properties are opposites depending on what your application is. Okay, you cannot say, okay, we want a higher mechanical property, we need a higher ultimate tensile stress, urine stress, but we need its conductivity is also higher. Okay, well, generously, it's not possible. It's not possible. Okay, therefore you have to specify what your application is. You're concentrated on the mechanical properties, mechanical strengths, or the electrical properties. Okay. If this give a summary that electroconductivity and resistivity are materials parameters, that means the materials properties. Okay, and the geometric dependence. Okay, geometry dependent. And electrical resistance are geometric and materials dependent parameters. Okay, therefore, resistivity is materials property, and the resistance is geometry dependent. Okay, that means we can measure it by multimeter. Okay, and conductor, semiconductor, and insulators differ in accessibility of the energy states for conductance electrons. For metals, conductivity is increased by reducing deformation, reducing imperfection, and decreasing temperatures. Okay, temperatures. Our electronic materials course ended here, and our course, material science, will be totally ended here. And if you have any questions, you can just leave your message or send me an email.